Hello, calculus fans. I'd like to go back to the problem that we discussed at the very beginning, where we said find the length of the curve y equals x squared between x equals 0 and x equals 2. And it mentioned that it's actually a very difficult problem in the sense that we didn't have a way of computing this at the time. And now we do have the tools to do it, so let's go ahead and calculate this. All right, so y prime is 2x. So we can put everything into the formula for the arc length, so integral from 0 to 2 of the square root of 1 plus 4x squared dx. All right, looks like a harmless integral, right? Well, we'll see about that. Okay, it's going to require an inverse trig substitution. If there was an x hanging out, we could just make an ordinary substitution, but it's not going to work out that way, so we do need the inverse trig substitution. Okay, so we're going to let theta be equal to inverse tangent of 2x over 1. Why 2x? Because we should think of the 4x squared as being 2x quantity squared. And then we have 1 is a squared, so we're substituting for u over a. So tangent of theta is equal to 2x, and secant squared theta d theta is equal to 2 dx. So we got 1/2 secant squared theta d theta is equal to dx. Okay, what else do we need? Oh, we don't know what that is. We're going to have to work that out with a triangle. Okay, so if we draw the triangle, if tangent of theta is equal to 2x, that means opposite is 2x, adjacent is 1, and that makes our hypotenuse square root of 1 plus 4x squared. So that tells us that secant theta is equal to square root of 1 plus 4x squared. We also need to change our limits of integration. Theta of 0 is equal to arctangent of 0, that's 0. And theta of 2 is equal to arctangent of 4. And there's no good way of simplifying arctangent of 4, so we're just going to have to leave it like that. All right, we're ready to put everything together into a theta integral. So we're going to have integral from 0 to 4 of secant theta times 1/2 secant squared theta d theta. Pull the 1/2 out, and we end up with the integral from 0 to arctangent of 4 of secant cubed theta d theta. Now this integral, it's on our list. It's on our list of integrals that we should have memorized. You may remember this came up when we did recycling. And one of the things I said at the time was it's probably worth your while to memorize this integral so we don't have to go do the recycling all over again. All right, so we get a 1/4 secant theta tangent theta plus log of secant theta plus tangent theta. That's evaluated from 0 to arctangent of 4. One thing to note is that, why is it 1/4? Well, when we did this originally, there was a 1/2 in there. So now we're going to plug everything in. We just get 1/4 of 4 secant arctangent of 4 plus log of secant of arctangent of 4 plus 4. You know, when you plug in arctangent of 4 into tangent of theta, you just get 4. But when we plug in arctangent of 4 into secant theta, what do we get? I don't know. We're going to work that out. What about the lower limit? Notice that secant theta tangent theta is 0, and log of secant theta plus tangent theta is equal to 0. All right, so the last thing we need is just to figure out what secant of arctangent of 4 is. The way we do it is we set up a triangle. We let phi be equal to arctangent of 4, and then we draw a triangle. So this is the triangle tells us the tangent of phi is equal to 4. So what if we want secant of that angle? Well, that's just going to be root 17 according to the Pythagorean theorem. All right, so that means this is our final answer. 1/4 times 4 root 17 plus log of root 17 plus 4. And I would say that's a pretty complicated looking answer for what I think is a pretty simple curve. Parabolas are pretty straightforward. So how did we get something so complicated? I guess that's just how the mysteries of math sometimes. Okay, that's all for now.